When we perform XPS, we expect to get chemical state information, and this is possible when we have a homogeneous sample. That's to say, elements are interacting with each other, different bond states, and when we try to perform our analysis of carbon or oxygen, we know that predominantly the chemical state between carbon and oxygen is the same over the entire analysis area. There are, however, samples such as this one where we may have chemistry of different types in different positions on the sample. So if we were to measure a survey measurement from the entire analysis area, we would end up with information that was not really providing chemical state information. It would be there, but it would be very confused and mixed between the different photoemission peaks. So in order to try and understand the chemistry of a sample such as this, what we're going to do is make use of techniques to identify areas of the sample that have a common composition, and therefore we can apply the principles of XPS to these different areas and come up with information that we would otherwise be unable to do if we just used a large area analysis. The individual images within this dataset do not include good quality signal to noise. So if we look at them as individual images, we'd find it difficult to identify the zones within the sample that we would like to analyze. Fortunately, we can use principal component analysis, and it will allow us to gather together all the signal from all the images at all the different energies and present the images that are the greatest variance within the data set in order. So overlaying all of these images in the active tile, you can see they're overlaid because they all have the yellow and the red border around the selected VAMAS blocks. I can press the OPS, Optimum Scaling Principal Component Analysis, where it will calculate 12 abstract factors, and then we'll be able to look at the top 12 abstract factors representing the greatest variance in the data. And once we have these abstract factors, it becomes more obvious where these different zones are. For example, here we have a zone that would predominantly be perhaps the glass. There's a shading here that is where I believe a gold wire resides, and then this dark area, this is a shading over the glass that is caused by a silver dag. The third abstract factor, well, this highlights a feature that is a gold wire. So these first three abstract factors are all enough to identify different zones within the sample. I'm going to return these to the raw state, and I've just copied over the three most important abstract factors. The objective in creating these abstract images is to identify different zones within the analysis area that we can assign to different composition of the sample. Here we have the silver dag, here we have the glass, and I'd like to identify these by their intensities. Previously I used a pattern that was predefined. There were a bunch of squares. 16 squares partitioned the image, and that had some benefit, but I can specifically pick out now where the silver dag is and where the silver dag is not. And that can be achieved using the color scales property page. I'm going to select the false color scale, and we can now see there's a good partitioning of these signals, but there is some overlap. So what I'm going to do before trying to partition is create a smooth of the image that will cause the zones to be more clearly delineated. So now I have a green zone that I think is silver dag, and all of this can represent the glass. I'll take a copy of that in the process form. So now I have a processed image that represents the smooth data. That's raw, this is now smoothed. So going back to the color scales, I've got a button here that says add false color, and what this does is it allows me to use the color scale to indicate a range of intensities. So I've picked out a range of intensities by drawing a box over the color scale that are consistent with this green zone up here, which I think is the silver dag. I then say add false color. I want one color, and I'm using the single color option. The range of intensities, these were gathered from how I marked out a box over this color scale, and when I say OK, we end up with a single color red over all of these pixels in this top right hand corner. So this ought to be the silver dag. Now let's do the same for the more intense pixels by selecting over the color scale a range of intensities and just say OK. You can see the values have been updated for intensity 1, intensity 2, one step, and we end up with two colors. So this represents a partitioning in terms of the second abstract factor into where I think there's silver dag and where I believe there's no silver dag. Let us now define this as the false color image. And what this will do is we'll create a false color mask that is specific to the pattern that we see here. Once defined, and I return these data back to the raw state, I can then use the sum spectra using colors. I've got two colors, so I should expect two spectra to be produced. This pink color is just the default. No pixels were assigned here, so this will not be used to create a spectrum. Only the red and only the green that I defined, and I say sum spectra using colors. And there we have one part looks like the silver dag, and the other part looks like that which is not silver dag. A little bit of silver here, so I didn't entirely partition the two sets, so we may need to do a little bit of more work on these data, but nevertheless I've achieved now a spectrum that looks very much like silver dag.